Hello and welcome back. Today we're going to be doing a walkthrough of the Edexcel 2024 Higher Paper 3. If you've got any specific questions you want to go look at, you can find the link in the comment section down below. But yeah, without further ado, let's go and dive in and we'll see what we can do. So, opening up the paper, here we are. Let's see what we can do. So, question number 1. Find the highest common factor between 63 and 105. So the way that we're going to walk through this is we're going to use the tree method. Potentially you could do this by just looking at the values and figuring out what the highest common factor is, but let's do it the more thorough way. And the way that we're going to do this is we're going to break it down into the prime factors of each value. And the way that we do this is we look at our numbers and we break it down into multiples that go into these values. So 63, what seems like a nice one to do here? You might know that 7 times 9 goes into this, and 7's a prime number, but 9 isn't just yet. Breaks further into 3 and 3. So these are going to be our prime factors. And then 105, well, it's in the 5 times table. Maybe we should do that. It's going to give 5 and 21, and then 21 into 7 and 3. Wonderful. So we can write all of these as their index form. 7 times 3 squared, and 105 is 3 times 5 times 7. Oh, I've put that. And then we're looking at the values that are common to both. So you'll notice that 3 and 7 are in both. And if we multiply these together, this is where you get your highest common factor from. Equals 3 times 7, so 21. Nice. Okay. Moving onwards, 5.34 times 10 to the 4 is an ordinary number. The way I like to do these is we're multiplying by 10 to the 4 in this case. We're making it larger. So for us, let's give ourselves some extra zeros afterwards just to play around with. And if we're doing 10 to the 4, that means that our decimal place is moving 2, 3, 4 places to the right. So our new value would be 53000, and then we are done, right? The new decimal place would be here, 53,000. We can apply the same logic to part 2, but this time we're multiplying by 10 to the minus 5. So instead of moving to the right, the decimal place, it's going to move to the left. So let's write this as 7.4. We're just giving us these sort of zeros as placeholders at the moment so we can move it. 1, 2, 3, 4. Oh, just giving myself just enough there. 5. So now we can basically look at it underneath. 0.0000074. Nice. Done and dusted. And then part B here. Calculate the value of 9.7 times 10 to the 6 plus 2.45 times 10 to the 7. Give your answer in standard form. This is probably the first time I'd be getting the calculator out. It is a calculator paper, of course. So I'm going to just type this in. 9.7 times 10 to the 6 plus 2.45 times 10 to the 7. You could, of course, do this in a more manual route. But I think for speed, it's definitely a little bit easier to just power through with your calculator. So we've got 342 with what looks like 5 zeros afterwards. So if we walk our way through backwards, we can break this down into our value. And we know for standard form, it's got to be one digit, point everything that's after it. And essentially, we're just going to count the number of places after the decimal place. So 1, 2, 3, 4, 5, 6, 7. 3.42 times 10 to the 7. Nice. Okay, question number 3. Rana is trying to draw the side elevation of a solid prism from the direction of the arrow. Here is her answer on the centimeter grids. Explain why the elevation is not correct. Okay, so it looks like we've correctly got 7 across here, but she's done 4 vertically here. But you'll notice that 4 isn't the vertical height. It's almost that diagonal height that we're looking at. So this 4 is incorrect. It would actually end up being whatever this vertical height is here. You'd probably have to do a bit of Pythag or something to figure that out. So here, I'd actually keep it super simple and just go incorrect vertical height. Nice. On the centimetre grid below, draw a plan of the solid prism. Okay, so a plan, going back to our diagram, the plan is what you'd see if you were looking from above. So we would see none of this 4 stuff going on, but we would see this rectangular base. Okay, think about it. You're looking from above. We're not going to see any of this shape, but we are going to see the 6x7. So all we need to do on here is draw a 6x7 diagram. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 6, 7. There it is. Perfect. There it is. Cool. Nice one. Next up, question 4. A company has 25,000 workers. The number of workers increases at a rate of 6% per year for 3 years. Cool. Calculate the number of workers at the end of the 3 years. So this is going to be an interest rate problem. We have a starting amount, 25,000. And we're going to multiply it by 1 plus the interest rate, 0.06, turning that percentage into a decimal, to the power of the number of years. There you go. This is a formula that's given to you in the formula sheet, so you can apply it straight away. But once we've done this, it's just about powering that through our calculator. When you look at that, we get 29,775.4. I suspect because you can't get half a person, they're just looking for 29,775. They haven't been explicitly clear about that, but yes. For 4 marks, I think that's quite a generous question. Okay, next up, we've got 2 identical tins. Okay, let's break this down a little bit further. He put 600 grams of flour into one of the tins. The flour fills the tin completely. The density of the flour is... okay. So this is looking like it's going to be a density equals mass over volume question. Okay. So we've got some information in this first section. Notice we've got a mass, 600 grams, and we've got a density. And it fills the volume completely. That's what this middle line is saying. So why not? Let's just figure out this volume straight away so we can use it later in the question. We're probably almost certainly going to have to use it. So volume is equal to, use your triangle here. A lot of people prefer using a triangle for these. And you'll notice that mass over density gives us our volume. So mass over density. So in our case, we've got the mass of 600 grams over 0.6 as the density. And notice, look, we're allowed to do this because our flour is in grams per centimeters cubed, and this is in grams as well. Sometimes you might have to change units here. So that's going to give us 600 divided by 0.6, giving us 1,000. 1,000 what? Well, once again, that's hidden in the units of density, centimeters cubed. Once again, be careful, pay attention to that. If they're not helping you out there, you need to keep an eye on the units. Okay, the second part of this question then goes on to say, Habib puts 600 grams of salt into the other tin. Okay, so for this part, we've got a mass of 600, and the salt does not fill the tin completely. Interesting. The volume of the space in the tin that is not filled with salt is 700 centimeters cubed. Interesting. So this is when we can work out the volume of space that is taken up. Well, we know that the total is 1,000 and 700 has not been used. So we're left with the salt only filling 300 centimeters cubed of the space. Our question now is to work out density. As we said to begin with, density equals mass over volume, which is going to be, in our case, 600 over 300, which hopefully you can spot quite quickly. It's just going to be 2. Nice. Question number 6, a probability tree. Is it dependent? No, it doesn't look like it. So we've got 2 bias coins, A and B. The probability of A landing on a heads is 0.6. Okay, very quickly we can go, the not heads is going to be 0.4, right? Probabilities have to sum to 1. And then that's all that's happening in this first bit of the tree. Then in the second section of the tree, we've got coin B flipping, and it's got 2 branches dependent on whether A was heads or not heads. The chances of it landing on heads is 0.55. This remains the same for both. There's no dependency here, which means that it not landing on heads is 0.45. Tim throws coin A once, and he throws coin B once. Work out the probability that both coins land on heads. Okay, so for this, we're going to be following the branches of heads, then heads again. And to think about it, we want to be multiplying down these branches. If that's not clear while you do that, consider maybe what all the other operators would do and why that would be wrong. Equally, I think a nice example is if you've got a fair coin and you were working out the probability of it landing on twice of a fair coin, it would be 50% in the first go and then 50% in the second go. In other words, 50% of 50%, which is a quarter, right? You're multiplying. So here, we've got a calculator, so we might as well do it as a decimal. 0.6 times by 0.55. And that's going to leave us with 0.6 times 0.55, 33%. It doesn't say the units, so you can leave this as a fraction decimal or a percentage. Nice. Okay, next up, we have a paddling pool in the shape of a cylinder. It has a radius of 100 centimeters and a depth of 30 centimeters. The pool is empty. It is then filled with water at a rate of 250 centimeters cubed per second. Work out the number of minutes it takes to fill the pool completely. Okay, so for this, we're going to have to work out the volume. And then notice we've actually got a unit inconsistency here. We've got per second filling here, and we want our answer in minutes. So we can come back to that later, and we're going to have to figure out how many minutes, not seconds, it's going to take to fill the pool. But let's start by trying to find our volume. The volume of a cylinder is the area of the two-dimensional shape at the top and bottom multiplied by the vertical height. This is true of all prisms. So we've got a circle at the top, so that's going to be pi times by the radius 100 squared multiplied by the vertical height 30. Cool. So this is our area, the pi times r squared, and the vertical height is 30. So let's see what that gives us. Pi times by 100 squared times by 30. Woohoo! 300,000 pi, or as an actual number, let's say it's 942,477.8. That's me rounding at this point, but that's the total volume, centimeters cubed. Now, we want to figure out the number of minutes it takes for us to fill this pool. And we've got an input of water at 250 centimeters cubed per second. But how much water would be filled in 1 minute? Well, to find that out, how many seconds are in a minute? 60. So if we do 250 times by 60, we're changing our units to minutes. 15,000 centimeters cubed per min. And now we basically just need to figure out, well, how many times does 15,000 go into this big old number? And then we'll get the total amount of minutes left. So if we do 942,477.8 divided by 15,000, we will get the number of minutes it takes for us to fill up this pool. 942,477.8 over 15,000, giving us 62.8 minutes. And we wanted it correct to the nearest minute, so 63. Nice, good. Careful with the units in that question. Okay, next up, a column vector question. On the grid below, draw and label the vector 2a plus b. Two ways of approaching this. Either that you can draw the vectors on individually on your diagram, or you can do the addition first with the scalar and draw it straight on. I will personally do the addition and figure out what vector this is going to be looking at our column vectors. So you want twice of A plus B. This is going to be the same as 2 times by both parts of the vector. So 6 over 4 plus minus 1, 4. And then with column vectors, you can just add across as you go. So we've got 5 and 8. That's it. So all we need to do, pick a point, go across 1, 2, 3, 4, 5. There's 5 across and up 8. 1, 2, 3, 4, 5, 6, 7. Oh, I've not given myself enough space. Let's move it down a little bit. We'll go here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So there's our vector. And that would be 2a plus B. Cool. Nice one. All right, on to question 9. Here we've got a square-based pyramid and a cube. The volume of the cube is equal to the volume of the pyramid. Okay, work out the perpendicular height of the pyramid. Oof. Okay, so things that we need to know. Volume of the cube, well, that's just all the sides multiplied by each other. But the volume of a square-based pyramid, that's a little bit harder. I believe it's given to you as a formula. So the volume is the base, right? So we could call this, let's call it the base squared times by a third of the vertical height. You don't need to know why this is, but it's good to be aware of that formula. I believe it's given to you. So we can work out both the volumes. This volume over here is going to be 6 cubed, which is going to be 216 centimeters cubed. And then over here, we're going to have 8 times 8, 64, times by some h over 3. But we know that this has got to be equal to 216, right? The volumes are the same. So now it's a case of figuring out how we can solve this question. In essence, we have 64 times by h over 3. So we're going to just have to rearrange this nicely. Let's see what we can do. So 216 divided by 64. So we'll get h over 3 is equal to 27 over 8. And now we can just multiply this by the denominator 3 over here. So times by 3, 81 over 8. In other words, do we need this as a decimal? No, we don't. But it's about 10.125 if you have it as a decimal. So yes, 81 over 8. Nice. Question 10. There are only red counters and yellow counters in bag A. Oh, okay. So in bag A, we've got red and yellow. The number of red counters to the number of yellow counters is 3 to 5. Okay, cool. There are only green and blue counters in B. Okay, green, blue. The number of counters in bag B is half the number of counters in bag A. Ooh. So let's make a note of that, half. Given that there are x red counters, use algebra to show that the total number of counters in bag A and bag B is 4x. Fascinating. So this is half, but we're never given the ratio in bag B, but does it matter? Well, let's find out. So we're being told that red is the equivalent of x. Okay. Now, I think a nice way to think about this is let's scale up. So we've got a slightly nicer transition here. Is that the nicest way of doing it? No, actually, I don't think so. I'd argue that the nicest way of doing it is treating 3 as though it equals x. Okay? So we can now say that red to yellow is going to be x, but what's going to be here? Well, actually, it's quite trivial, isn't it? It's just 5 over 3x, right? How do we get to 5 from 3? Well, 5 over 3x. So if this now constitutes the total amount of counters in bag A, we can say that in A, we've got x plus 5 over 3x. In other words, this is going to become, what's that going to be? We've got 3 over 3 here, so we're going to have 8 over 3x. Now, if half of this is in bag B, well, then we know that we're going to have 4 over 3x. And now we can just add these two together. 8 over 3x plus 4 over 3x equals 12 over 3x, which is 4x. Question 11. Mina records the speed in miles per hour of some cars on a road on Friday. She uses her results to make a box plot. Okie dokie. Yeah, we've got lower speed, lower quartile, median, interquartile, and a range. Okay, so we're only missing our highest speed here, but we can work that out using the range. So 25, that's going to be right there. A lower quartile at 35, cool. Another line there. A median at 40 there. Interquartile range, yeah, we're going to need to find our upper quartile. So 35 plus 12 gives 47. So that's fine, 47. There it is. Draw ourselves our box in the middle. And then our range, we've got 25 plus 37 from the minimum value plus the full entire range. 25 plus 37, no point dwelling on that. 62. Fantastic. So there's our upper. Whabam, donezo. Mina also records the speeds of some cars on the same road on Sunday. Compare the distributions. How many marks is this? 2 marks. So we want to make 2 comparisons. The most notable comparisons I see straight away is actually the median has increased and our highest speed has also increased. So let's just make some direct comparisons on those. Friday has a lower median, 40, compared to Sundays. What's this? 42. Equally, Friday has a lower top speed of 62 compared to Sunday's 66. You could then go on to say that overall it appears that Sunday's faster than Friday. The diagram shows triangle T drawn on a grid. Enlarge triangle T by a scale factor of -2 around the point 0, 0. Cool. Okay, so a scale factor of enlargement from a specific point. There it is. There's our point. The nicest way to do this is usually using straight lines. You can get a ruler out, map a straight line from multiple points, and see where they go through the other side of the point. Unfortunately, I don't quite have this luxury on here, so I'm going to do it a slightly more manual way. We're going to take this point and we're going to reflect this. So currently it's going 1 to the right and 3 up. Okay. But if we were to reflect this, it's going to go 1 to the left and 3 down. Right? So the point would be here if we had a scale factor of enlargement of -1, but we actually wanted a scale factor of enlargement of -2. So we just repeat this exercise again from here. 1 across, 1, 2, 3 down. So that point goes there. I'm going to repeat the same thing with this point over here. I'm not very well there, but that's okay. 1, 2, 3, 1, 2. That gives us this point. I'm going to do it in blue so we can see the difference a bit more clearly. 1, 2, 3, 1, 2. That gives this point straight away. 1, 2, 3, 1, 2. That would be over here. Using those 2 points, we can roughly see how the shape's going to look. So we can kind of just draw it on from here. Remember, it's reflecting as well. So actually, it's going to appear upside down over here. There's our new shape. Cool. Yeah, nice. Okay, it's done. There are 30 students in a class. A teacher is going to choose at random 2 of the students. Work out the number of different pairs of students that the teacher can choose. Okay, so there are 30 students. And if you were each of those students, let's name them. So if you were student A, right, and this goes all the way through to like, I don't know, there's only 26 letters in the alphabet, isn't there? So maybe we've got some Greek letters at the bottom, but let's say Z, right? And person A could be paired with any of the people B and onwards. They can't be paired with themselves, can they? So if this list is 30 long, and the list of pairing people that they could be with, let's say B to Z, well, this is only 29 long, right? You've got to factor in all of those combinations for everybody. So all of the branches, all the possible opportunities is going to be 30 times by 29. But the problem is, though, is that by doing this, we're factoring each branch twice, right? Notice A to B's got a link, but we could also go, oh, well, B would map to A, then to C, so on to Z. So B maps to A. Every single branch is getting mapped twice. So to get past this, all we're going to do is do 30 times by 29 divided by 2. That'll give you your answer. So 30 times by 29 equals divided by 2, 435 combinations. Wonderful. Question 14. At the start of 2022, Kim invested some money in a savings account. The account paid 3.5% compound interest each year. At the end of 2022, interest was added to the account. Then Kim took £750 out of the account. Ooh. At the end of 2023, interest was added, and then she took out 100. There was 2,937.14 in the account. Okay. Fascinating question. Cool. Okay. So we're going to have to work backwards through our equation. But to do this, let's try and map out how it would work to begin with. So, to begin with, she invests X. Okay? She's then going to get this 3.5% interest. So this is going to multiply by 1.035. Okay? So this is now going to be the amount that she has at the end of 2022. Okay? And at this point, she took out 750. Let's call this Y. So that means that she starts 2023 with Y minus 750. She then gets her 1.035 again, and this would get you to the end of 2023. And then she took out 1,000. And let's say that after she's taken out that 1,000, we're left with Z, right? But Z is this amount here. Okay? So, how can we work backwards through this? Well, to find the amount that she had at the end of 2023, we need to take this 2,937.14 and add 1,000. That's going to get us to here. Oh, that's 100. So let's have a look at this. 2,937.14 plus 1,000. Hopefully pretty easy. It's going to be 3,000. 3,937.14. Cool. And now we can start solving this equation for Y. So let's start rearranging. So this value is currently here, if we're thinking about it. So Y minus 750 times by 1.035 equals 3,937.14. We can divide by the 1.035. Y minus 750 equals 3,937.14 over 1.035. Let's do that. 1.035. And then to get Y, we're going to just add the 750. So we get 3,804 plus 750 equals 4,554. Cool. And remember that this value of Y is what we stated was going to be here. And then just to get X, all we need to do is take that 4,554 and once again divide it by 1.035 to get back to X. So divided by 1.035. Wonderful. £4,400. That's not easy. There's a lot of stuff going on there. Okay. On to some algebra here. Simplify fully a minus 3 squared over 5a minus 3. Cool. This is the same as having a minus 3 on the numerator, and then 5a minus 3. And hopefully you'll notice, regardless of the value of a, one set of these brackets is going to cancel, leaving you with a minus 3 over 5. Woohoo! Factorize 3k squared plus 11k minus 4. There's a few different ways of factorizing these sorts of questions and methodologies. There is a set standard methodology that you can use that will always give you the right answer. There's also the trial and error method. And I think more of you guys will probably be using a trial and error method. So that's what I'm going to use here. We can say that we've got a pair of brackets like this. And we know that the two k values at the start must give us 3k squared. Start thinking about what two values must multiply to give us that 3. We can then apply the same logic to get this minus 4. Two values are going to have to give us that minus 4. Now, thinking really smartly about this, the red values, you can only have a 3k and a k. That is the only combination of values you can have. But for the blues, there's a bit more. You could have 4 and minus 1. You could have minus 4 and positive 1. You could also have minus 2 and 2 and 2 and minus 2. So our objective is just to run through all of these combinations and see which one would give us our 11k in the middle. So we've got 3k and k here. Now, if we think about this really quickly, we're going to be doing 3k times the value here and k times by the value here. So let's run through these and think about which ones would work best. So 3 times minus 1 plus 4. Does that give us 11? No. What about if we did this the other way around? 3 times 4, take away 1. Absolutely, that works. So we can have plus 4 minus 1. Yes, and actually, sorry, something I should have made a little bit more clear is we've got to consider these both way rounds, because this 3k can affect the 4 proportionally more. There you go. Cool. You may have had to have run through this a little while, but think about it, right? You want a positive value. So you want this 3k multiplying a positive number, and then the k probably a small negative number. So there you go. Last on the table, we've got simplify fully this division. Let's start by mapping this out. So we've got 4 minus x squared over x squared plus 3x. Remember, you've got a division here, so that's going to flip our fraction to x plus 3 over x plus 2. Then we can factorize both the things on the left. Notice on the right, everything's fully factored already. The numerator is a little bit hard, so I'm going to start with the denominator, which gives us x plus 3. And then the numerator. This is a little bit weird. Let's rewrite this. I'm going to do it to the side in red. We've got 4 minus x squared. Now, for peace of mind, I'm going to rewrite this as minus x squared plus 4. Now, only because this looks a little bit more like a quadratic you would normally have seen. Now, let's think about it, right? What two values have to multiply together to give minus x squared? We know this is going to be a quadratic. Just, yeah, go with the flow. Well, it's got to be x and minus x. And then what two values multiply to give positive 4? Plus 2 and plus 2. And lo and behold, you're left immediately with your factorization. This is dots under the cover, okay? Difference of 2 squares. So we end up with x plus 2 minus x plus 2. A little hint as well is that you know there's going to be a cancellation with the values over here. So once again, multiplying by x plus 3 over the x plus 2. Putting things in brackets to make it really explicit. Let's put this all together now. You know when multiplying fractions, you can just put the numerators together, put the denominators together as though they're multiplying. So on the top, we'd have x plus 2, minus x plus 2, x plus 3 over x plus 3, x plus 2. And let's just cancel out everything that's the same. So we've got this x plus 3 here, this x plus 3, x plus 2, x plus 2 goes. And you are left with minus x plus 2 over x. And arguably you could take that a slight step further and break it into 2 fractions. And I'm going to do this in blue. This is a valid answer, but you could take this a step further and say that this is minus x over x plus 2 over x, which is the same as minus 1 plus 2 over x. Nice. Question 16. Functions f and g are given by those two equations. Find f if you replace x with minus 3. Okay, wonderful. 12 over minus 3 plus 1. 12 over minus 2 equals minus 6. Find f of g of 1. F of g is what happens when you replace the x value in f with the function g. In other words, 12 over 5 minus 3x plus 1. This is f of g of x. And now we're thinking about, what happens when I replace that x value with 1? I would get 12 over 5 minus 3 plus 1, which is the same as 12 over 2, 3, which is 4. And find the inverse of g, and then substitute the x value with 4. G of x equals 5 minus 3x. Equals 5 minus 3x. And we want to inverse it to begin with. The way that we do this is we set our variables back to y, 5 minus 3x. And an inverse is essentially flipping around your coordinates. So to do that, we do, in essence, just flip around the coordinates. X equals 5 minus 3y. But we're going to solve getting ourselves back to y now. So we've got y equals something. That'll get us back to an equation. So x minus 5 equals minus 3y. And then we're going to divide by minus 3. So y is equal to x minus 5 over minus 3. Cool. And now, just to figure out what our g minus 1 of 4 is, all we're going to do is substitute in the 4 into this equation. And figure out what it equals. 4 minus 5 minus 1 over minus 3 is going to give you a third. Nice. Question 17. A ball is thrown upwards and reaches a maximum height. The ball then falls and bounces repeatedly. After the nth bounce, the ball reaches a height of h. After the next bounce, the ball reaches a height given by hn plus 1 equals 0.55 of hn. Seems a little bit overcomplicated, right? But what it's saying is that each subsequent bounce is going to be 55% of the previous bounce. After the first bounce, h1, the ball reaches a height of 8 meters. What height is it after the fourth bounce? Honestly, I wouldn't overcomplicate this. Don't try and do any clever maths. So let's just analyze the situation. So what we've got here is that each subsequent bounce is 0.55 of each bounce afterwards. So let's draw a little bit of a diagram. You've got 8 meters on the first bounce. And then the second bounce is going to be slightly less. It's going to be 0.55 of what we had previously. So we can just do 0.55 times 8, and that's going to give us 4.4 meters. And we're just going to repeat this process a couple more times, and we'll figure out what we've got. Times by 0.55, that gives us 2.42 meters. And last but not least, we're going to have the last one times by 0.55. It's going to be 1.331. Nice. Question 18. We've got some weird looking quadrilateral that's been split into two triangles. The area of triangle ABC is 54 centimeters squared. Calculate the area of triangle ACD. Very cool. Right, we've got not equal triangles here, do we? They're not right angled. So that means to find our areas, we're going to be using the trig formula, half AB sine of angle C. So our objective is to find the size of this triangle over here. But to do that, looking at our formula, we're going to need two side lengths. We currently have two angles, right? So we need to find two side lengths in here that we don't currently have. Sine C, that can happily be any of these two angles that we've already got, or even this one. So how can we help ourselves here? How can we make life a little bit easier for us? Well, I would say that we know originally that the area of triangle ABC is 54 centimeters squared. Let's write that in there. So this is 54 centimeters squared. And we know that the area of this is also derived by this formula, half AB sine C. We've got a side A, and we've got an angle, C. And remember that this means that it's opposite this side. We'll call this one C, which means that the other side length must be this one. So we can figure out this side length here by using the formula, a half times by 17 times by some unknown. Let's keep it as B in this case, length B, sine of 35 equals 54. Okay. So let's run through this thing. Let's rearrange. So a few different ways you could do this. I'm going to kind of just run through it in one go. So a half times 17 times B is going to be 54 over sine 35. Then we could also divide by that 17. A half times by B is equal to 54 over 17 sine 35. And then we can get rid of the half by multiplying by 2. So B is equal to 2 times 54 over 17 sine 35. Okay. Let's power that into our calculator. 2 times 54, 17 sine 35. Wonderful, giving us 11.076. Yeah, let's give it to a few decimal places in this case, so we're not accidentally messing up our answer to three significant figures. So we've got 11.076. 0.076 here. Okay, cool. So we're getting a little bit closer to our answer. But remember, to find the area of this shape over here, this triangle, we're going to need two sides and one angle. Now, what I've quickly spotted is that actually we're very close to being able to find the side length over here. We can do this using the sine rule, because the sine rule requires one set of an opposite angle and side, and another set where you're missing one of the values. So we can figure out this green length using the sine rule. I'll run through this with a green bit of maths. So we've got our x value, let's say it's that length, over its associated angle, sine 48. And we know that this is going to be equal to the length that we just found, 11.076, over sine of 57. We can rearrange this so that x is equal to sine of 48 times by 11.076 over sine of 57. Cool, let's power that into our calculator. So sine of 48 times by the 11.076 times divided by sine 57, giving us 9.814. I'm going to do it to 3 decimal places again. So 9.814 up there. Cool. Okay, it's all looking good. We've now got two sides, but the problem is that well, they're both the associated angles. So we're going to need a new angle, but thankfully the world is coming in useful here. We've got a triangle. We know that triangles add to 180 degrees on the inside, so we can figure out that angle in the corner very quickly by doing 180 minus 57 minus 48, giving us 75. And now all we need to do is pass in all of these values that we've just found into our equation. Half times by 9.814 times by 11.076 times by sine of 75. And if we do that, half times by 9.814 times by 11.076 times by sine 75 gives us 52.498. Our question asked it to 3 significant figures, so this figure is the one that we're interested in, 52.5. Nice. Question 19. We've got P correct to 3 significant figures, and we've got Q equal to 3.6 times 10 to the 5 correct to 2 significant figures. Figure out the lower bound of R. We want to know what the lowest value R could be. R is equal to P over Q. And to minimize the value of R, we want to find the min of R. Well, to do that, we want to find the minimum this fraction can be. Now, be careful with how you do this. We want to have the min of P, the smallest numerator, the smallest number of slices, over the maximum of Q. Okay, we want the biggest value of that denominator. That's going to make the distance between the two values as big as possible. Cool. So let's think about this. What's going to be our minimum of P? Well, rounded to 3 significant figures, this can become 5.875 times 10 to the 8. And our denominator, rounded upwards, can become 3.65 times 10 to the 5. Our standard form figure's not changing because we're not messing with the decimal place. Cool. So we can just power this into our calculator, put it in there, and we can figure out what value we'd get from that. So times 10 to the 5. Boom. Does it want it in standard form? Give your answer as an ordinary number. Wonderful. To the nearest integer. So I got 1609.589. So that would be 1609.6. Oh, nearest integer, I'm being silly. So that rounds up to 1610. Nice. Fantastic. That's all going very well. Onwards we go to question 20. X minus 4, x plus 2, and 3x plus 1 are 3 consecutive terms of an arithmetic sequence. Okay, that means that they're being added or subtracted between terms. Find the value of x. Okay, cool. So let's have a think about this. So we've got x minus 4, x plus 2, and 3x plus 1. And we're adding or subtracting a value consistently between terms. We're going to be adding, let's say, plus some value plus some question mark, right? Plus some question mark. Now, it's actually quite clear in this first step what we're adding, because we're starting with x, and regardless of what value of x, well, we're at -4, and then we get to +2. So adding 6, this must be 6. Which means that this must also be +6, or else it wouldn't be an arithmetic sequence. So let's analyze the situation here. We've got x -4 gets to x +2, and this is a distance of +6. But going from x +2, and if we add 6, this must be equal to 3x +1, right? So we're turning that idea into an equation for us to solve. So x +8 must be identical to 3x +1. Let's rearrange this so everything's all working out nicely. Take the 1 from the left-hand side, 7. Take away the x, move it to this side, 2x. Therefore, x is equal to 7/2. Onto this one, we've now got a geometric sequence. So geometric, differently to arithmetic, means that you're multiplying or dividing. Now, this is a little bit harder, but we can figure it out. So that means to get from y -4 to y +2, we've multiplied by some value r. And then once again, to get to 3y +1, we've multiplied by another value of r. So you could argue that r times by y -4 equals y +2. That makes sense? R times this thing is this thing. Similarly, r times by y +2 is equal to 3y +1. We can now isolate r in both equations. R is equal to y +2 over y -4. And over here, we've got r is equal to 3y +1 over y +2. And now, because they're both equal to r, we can set them equal to each other. Amazing. So we get rid of our value of r, and we've got y +2 divided by y -4 equals 3y +1 over y +2. Okay, so now we're into the nitty-gritty of the algebra. Gosh, 5 marks for that question as well. So this is not a small bit of algebra to figure this out. The next step that I'd advise is we're going to what's known as cross-multiply. Remember, if you've got a denominator in a bit of algebra and you don't want it there, you can just multiply the whole thing to the other side. We're doing that simultaneously to both sides. So we'd end up with y +2 equals 3y +1, y -4. Fantastic. We can now expand, move everything to one side, turn it into a quadratic equal to 0, and solve for our value of y. So on the left-hand side, we're going to get y squared plus 4y plus 4. On this side, we're going to get 3y squared minus 12y, and then we're going to get, what are we going to get? Plus y minus 4. Okay, so at this point, we've got 3y squared, take away y squared. Therefore, we're going to end up with 0 equals 2y squared plus 4. And then over here, we've got minus 11y. All right, so minus 11y, and we're taking away this 4. So we're going to be at minus 15y. And then we've got minus 4 on this side. We've got positive 4 on this side. So we're going to take away the 4, giving us minus 8. Wonderful. And now it is our objective to figure out what brackets are going to make this work. A few different ways of doing this. Quite often, I suppose, you'd end up looking at this and just going, what could possibly work? If you've got one of those fancy calculators that solves for you, you can do it that way. I'm going to just spend a little moment explaining how I'd probably go about this. You're going to need 2 brackets. Once again, you're going to need the values to the left to equal 2y squared, and you're going to need the brackets on the right to equal minus 8. So thinking about this, the only possible values you could have for your red are going to be 2y and y. And then the values for your blue, well, you want it to be combinations that multiply to be minus 8. So we're thinking about 8 and 1, and then we're thinking about maybe 2 and 4 as well. Now, we want to make sure that our final value that we get in the middle is minus 15y. And actually, this gives it away quite quickly. The only way to do this is 2y minus 8, right, giving us minus 16, and then adding the 1 to the other side. So plus 1, right? Y times 1 is 1y. 2y times minus 8 is going to be minus 16y. Cool. So from here, we can now figure out our actual values by solving these things. So we've got 2y plus 1 is equal to 0. Remember, this whole thing's equal to 0. So we're going to get 2y equals minus 1, therefore y is minus a half. Or on this side, we've got y minus 8 is equal to 0, so y is equal to 8. And there's your two answers. Y is minus a half, or y is equal to 8. Fantastic. And then question 21. Ooh, this is very interesting. We've got a circle, and it's got two hexagons, inside and outside. Interesting. This is very interesting, a sort of Euclidean model here that a lot of you might not have seen. So we're going to have to really sort of tackle this very abstractly. And we've got a target. By considering perimeters, what a wonderful hint that is. Consider perimeters, show this. So actually, the nicest thing to do here is just figure out what each of our perimeters would be. We've got three things, right? We've got an inner hexagon, a circle, and an outer hexagon. So let's just start by defining our circle. What would you say the perimeter of a circle is? Well, it's just the circumference, right? What do we know about the circumference? Well, the diagram shows a circle with radius r. Wonderful. So our circle's perimeter must be 2 pi r. Okay, take that, note that, that's going to be rather useful. Let's now do the inner hexagon. Okay, so thinking about this, right, we've got a point, and we know that the radius of the circle must be r. So this distance from the center to, say, P must be r. But the distance from, say, the center to this point U is also r. Well, that's kind of interesting. What else do we know? Well, we know that the angle on the inside here must be 60. Why 60? Well, think about it. There are 6 sides to this hexagon. And we know that the distance all the way around from a point is 360. So to get this angle on the inside, 60 degrees. Now this is starting to sort of hint that something interesting is going on. This could certainly be an isosceles triangle, right? Because we've got two lengths that are the same length, r and r. With isosceles triangles, that means that the two remaining angles must be the same length. But of course, this one's 60, so these must both be 60. And not only is it isosceles, it's therefore equilateral. This length over here is therefore r, right? Each of the angles is the same, therefore each of the lengths must be the same. That's the fact about equilateral triangles. So wonderfully here, this value has just fallen out. This value to one side over here is, in fact, r. We've got 6 of them, right, to get all the way around. So therefore, the inner hexagon has a total perimeter of 6r. Fantastic. Now, let's focus on the outer sides. Now, this is a little bit harder, but we can analyze it in a very similar way. A little hint for us is going to be that, well, once again, all the way to the outside, let's denote this as maybe point x. This is still going to be r. But what now? What can we do to find this length? Well, if we were to draw another line, we've now got a right-angled triangle. We know the bottom is r. We don't quite know the length of the hypotenuse. Remember, from the origin, the midpoint here to Q, that would be length r, but we've got this extra little bit of space to the outside. But does it matter? If we can find this length here, right, well, then we can double it to get the entire side length. And then we just need to multiply it by 6 to get each of the sides. In other words, if we can find this side length and multiply it by 12, we've got the perimeter. Wonderful. So how are we going to find that side length? Well, we can't use Pythag because we can't possibly know what that hypotenuse is. But we can, using a bit of SOHCAHTOA trig and this angle, work out this length. Now notice that previously we considered that this whole length side over here, matching over here, right? This had an angle of 60. A hexagon has 6 sides, and therefore dividing the total circle into 6 gives us 60. But we've got half of that now, right? We're taking half this, so this must be 30. So we can figure out using SOHCAHTOA that this side over here is going to be an opposite and an adjacent. Think TOA. And therefore, this side over here is your opposite, your r is your adjacent. We want r times by tan of 30. Now if we do tan of 30 on our calculator, we get root 3 over 3. So we find that this red length over here is going to be r times by root 3 over 3. How cool is that? But here's the interesting bit. To get our total perimeter, we must multiply this by 12 because we're going to have 12 as these segments going all the way around, right? There's going to be 2 of these segments between B and C, and there's 6 sides altogether. So we can then go and say that the outer hex is going to be equal to 12 times by r root 3 over 3. And this, if we do this quickly on our calculator, is the same as 4 root 3. So we end up with 4 root 3 times by r. Okay, so we found the perimeters of each of the shapes. We found the circle, the inner hexagon, and the outer hexagon. How are we going to make this inequality, though? Well, it's quite clear that the inner hexagon has got shorter distances between these points where it meets the circle. So its perimeter must be less than the circle. And similarly, using the same logic, well, the outer hexagon has to go slightly further. It can't cut the corner, right? Between here, the outer hexagon has to go the long way. So its perimeter must be longer. This is starting to look very similar to what we're looking at. Is there a way we can simplify this? Well, absolutely. Each of these values have got r in them, so we can cancel all of these r's, and then each factor is a multiple of 2, so we can divide everything by 2, giving us 3 is less than pi is less than 2 root 3. A fantastic proof, I believe, by Euclid. You can actually take this to a logical extreme as well, making slightly more, like giving sides giving shapes with more sides on the inside of the circle and on the outside of the circle, and you'll get a progressively more accurate estimate of what pi is. So you can take this to the logical extreme and get a very, very strong estimation for what pi is. A wonderful question. Very hard, ought to be worth them 4 marks. But there you have it. We've powered through the whole of this paper, I think in just under an hour as well. That's very good pace. I hope that was useful. If you've got any further questions, or you maybe did a question in a different way, let me know. That's really cool. Equally, look, if you've got questions, drop them below and I'll do my best to get back to you straight away. Excellent stuff, guys. Take care, and I'll see you in the next one.